Welcome to this session on recursive algorithms, a fundamental concept in algorithm design. In this lecture, we will understand what a recursion is and how recursive algorithms work, analyze their time complexity, and apply them to common problems like factorial, Fibonacci, and sorting. I am Satyapriya, Assistant Professor, Department of Information Technology, K.S. Rangasamy College of Technology. Introduction to recursive algorithm. Recursive algorithms call themselves with smaller inputs, widely used in problems like divide and conquer, searching, sorting, dynamic programming. Example, factorial algorithm, f of n. The algorithm is compute and factorial recursively. The input is non-negative integer n, the output is n factorial. The algorithm is if n equal to 0, then return 1, else the return f of n minus 1 star n. Factorial algorithm recurrence relation. So we have the recurrence relation for this factorial algorithm is f of n is equal to f of n minus 1 star n for n is greater than 0. The base case is f of 0 is equal to 1. The number of multiplications m of n is equal to m of n minus 1 plus n for n is greater than 0. Solving recurrence for factorial algorithm start with m of n is equal to m of n minus 1 plus 1. Use backward substitution. So m of n is equal to m of n minus 1 plus 1, which is equal to m of n minus 2 plus 1 plus 1, m of n minus 2 plus 2. The general formula for this recurrence relations of factorial algorithm is m of n is equal to m of n minus I plus I. For I equal to n, m of n is equal to n. Efficiency of a recurrence algorithm is used to define the parameters indicating input size. Example, n. Identify the basic operation. Usually the innermost operations in the recursive call. Determine how the number of operations scales with the input size. Analyzing the recursive algorithm efficiency, set up a recurrence relation for the basic operation, solve the recurrence or determine its order of growth, analyze worst case, average case, and best case scenarios. The example 2 for this recurrence relation algorithm is Towers of Hanoi problem. The problem is move n disks from one peg to another using recursion. The rules for this Towers of Hanoi problem is only one disk can be moved at a time. The larger disk cannot be placed on a smaller. The solution for this Towers of Hanoi recursive algorithm is for n is greater than 1, move n minus 1 disk from peg 1 to peg 2 using peg 3 as auxiliary. Move the largest disk from peg 1 to peg 3. Move n minus 1 disk from peg 2 to peg 3 using peg 1 as an auxiliary. The recurrence relation for this Towers of Hanoi is the input is number of disks n. The basic operation moving one disk. Recurrence m of n is equal to 2 into m of n minus 1 plus 1 for n is greater than 1. The initial condition is m of 1 is equal to 1. Solving the recurrence of Towers of Hanoi, start with m of n is equal to 2, m of n minus 1 plus 1. Use backward substitution. M of n is equal to 2, m of n minus 1 plus 1. 2 into m of n minus 2 plus 1 is equal to 2 power 2m n minus 2 plus 1. The general formula for this Towers of Hanoi solving recurrence relation is m of n is equal to 2 power n minus 1. The time complexity is order of 2 power n. Towers of Hanoi time complexity, which is used to find the problem. Instinct difficulty makes the algorithm exponentially complex. Time complexity is order of 2 power n. The exponential growth due to the recursive nature of the problem. Third example for this recursion is binary representation. So the algorithm is compute the number of binary digits in a decimal integer n. Input a positive decimal integer n. The output is number of binary digits in n's binary representation. Binary representation recurrence relation. Recurrence A of n is equal to A of floor of n by 2 plus 1 for n is greater than 1. Base case is A of n is equal to 0. Analyzing binary representation algorithm. Use backward substitution. The general formula for this binary representation is A of 2 power k is equal to k. The time complexity is order of log n. Solving binary representation recurrence, we have the complexity order of log n. So we have the following exercise to solve the problems. So these are the examples for the practice. So these are the examples to be continued. The solution for the examples of x of n is equal to x of n minus 1 plus 5. The base case is x of n is equal to 0. X of n is equal to 5 into n minus 1. The solution of the example 2 is 4 into 3 power n minus 1 plus 5 into 3 power n minus 2 plus so on. The conclusion, recursive algorithms are fundamental in algorithm design, but their efficiency can be complex. Analyzing recursive algorithms involves solving recurrence relations and understanding their time complexities. Questions for further discussion? Thank you.